Alright, so before we look at some detailed examples, I want to try to help you understand the concept of related rates. So let's imagine this is your house, and this is where you and your parents leave from in the morning. And let's imagine you leave at the exact same time. So this is your starting location. You are here at time 0. And let's say that you head east to school. So here's school, and here's you in your car heading east. And your parents, they leave at time 0, but they head south to work. And let's say 10 minutes later, I could tell you exactly how far you are from your house. So this moment in time is when t equals 10 minutes. And let's say at 10 minutes, you are exactly 4 miles from your house. And I'm going to go ahead and call that distance x. And then let's say at time t equals 10 minutes, we could figure out that your parents' distance from the house was 3 miles. So let's go ahead and say the distance from the very back of the car. So let's just try to make it really specific. So at 10 minutes, you are 4 miles from the house. Your parents are 3 miles from the house. Now, if I was interested in finding the distance between the two of you, between you and your parents, the straight line distance, I could connect these two dots together. And to find that distance, I could recognize that because your parents are heading perfectly south and you're going perfectly west, east, this forms a right triangle. And so to find this distance, let's go ahead and call it z. I could use the Pythagorean theorem. So I'm going to go ahead and call this y. The Pythagorean theorem would tell me that x squared plus y squared equals z squared. So this Pythagorean theorem is a way to relate distances. So if I were interested in finding the distance, so this hypotenuse of the Pythagorean theorem, I could plug everything in. So x is 4, y is 3, and I'm solving for z. So this is 25. So taking the square root of both sides, I would get plus or minus 5. But since z is a distance, z is just positive 5 miles. So notice I had a known geometric equation that allowed me to relate two distances together using a right triangle's geometry formula, the Pythagorean theorem. But at 10 minutes, not only can you tell exactly how far you are from the house, let's say, and exactly how far your parents are from the house, let's say right at 10 minutes, we looked at the speedometer. And we knew exactly how fast you were going at 10 minutes. So if right at 10 minutes we looked at the speedometer and you were going 40 miles per hour, so what that would translate to mathematically, and I'm going to change colors here, is that at this moment in time, you were traveling at a rate, so since this distance is x, the rate at which x is changing, the distance from the house right at this moment, the rate that the distance is changing is, we said, 40 miles per hour. Or miles per hour could be thought of as miles over 1 hour. So this is clearly a rate. And right at exactly 10 minutes, I could also figure out exactly how fast your parents were going. If we call this distance from the house y, then they are traveling at a rate of dy dt, which we just said was 30 miles per hour. So if we can find the exact rate of change that you were traveling at 10 minutes and the exact rate of change your parents were traveling at 10 minutes, then we can find exactly how fast the distance between you two is growing. So not how far apart you are. How far apart you are isn't a calculus question. That's a pre-calc question. That's using the Pythagorean theorem. So at 10 minutes, I know that you're 5 miles apart. But the question would be, how fast is the distance between you changing? What is the rate of change of the distance between the two of your cars? So in other words, the question that we're going to be asking is, what is dz dt at 10 minutes? This is the notion of related rates. We're trying to relate two rates together using known geometric formulas. So we can already relate distances using the Pythagorean theorem or other known geometric formulas, but now we want to go one step further and relate the rates of change at particular moments in time. So I would have to know exactly how fast you're going and exactly how fast your parents are going right at 10 minutes in order to be able to figure out the rate of change of the distance between the two of you. So this is what our goal is going to be in this section on related rates. Alright, now let's go over the general strategy for solving a related rate problem. So the first step, of course, is to read the problem carefully, and you'll typically need to go through it at least twice to get all the relevant information out. So once you've done that, the best thing to do is to draw a diagram or a picture, and this is typically going to be a geometric shape of some kind. Part 3, once you've drawn your picture, you want to assign variables to all quantities that are changing and label all constants in the picture. So not everything is going to be a changing quantity. So when something is changing, we're going to have to label it a variable like x or y. But sometimes things will remain constant, a constant height or constant length, and then we can just go ahead and fill in that constant number in the diagram that we've drawn. Step 4. Write the givens and the wants in mathematical notation. So these will likely be rates of the form dh dt, dr dt, d theta dt, dy dt, etc. So often we are given a rate of change expressed in words, and we have to translate that into mathematical notation of this form. So d something dt, and then we need to figure out what we want. What are we being asked for? And we might also be given constants, not only rates. So constants would be of the form x equals, r equals, or h equals. So we really have to distinguish between whether they've given us a quantity or a constant versus a rate. So those keywords like per, in, or for are going to tell us we've been given a rate. Number 5, write a general primary equation that relates the variables in the problem. And here you will likely be using geometry or trigonometry. So we want to somehow write an equation that relates the variables. So like in that previous example, we went to the Pythagorean theorem that was a known geometric formula that related the sides of a right triangle. So this is typically going to be one of the harder parts of the problem, is figuring out how to relate the variables so that we can eventually take its derivative. Now, part 6, if any quantities in the equations are constant, then you may replace the variable with the constant number. So if you haven't already labeled the constants in the picture, you can replace any variables with constants if those are not changing quantities. Otherwise, leave all the variables in the equation. And then this is sort of a little 6a or a side note. You may need to use geometry to manipulate a formula to eliminate an unwanted variable by substitution. So this gets into a trickier type of related rates problem where maybe you have one too many variables and you don't have enough information, so you have to use geometry or other tactics to get rid of that variable that you don't have any information about. Number 7, use the chain rule and implicit differentiation to differentiate both sides of the equation with respect to time. So once you find the equation, then it's a matter of correctly applying implicit differentiation. And in part 8, we substitute in the given data. So you found your givens in part 4. So once you take the derivative, you substitute in your givens and you solve for whatever you wanted, whatever that unknown quantity is. And then step 9, round your answer to 3 decimals, include units, and make sure your answer makes sense. So in calculus, we need to always make sure that we go out to the thousandths place. So what I mean by 3 decimals is 3 places past the decimal. We always have to include our units. And then you want to make sure your answer makes sense. So I always give the example of sometimes I have students say the car was traveling 450 miles per hour. So that definitely doesn't make sense. So once you're done, and you box in your answer, you go back and reread the question again and make sure that in the context of the problem, your answer makes sense in the real world. Alright, now let's look at a pretty basic example. Example 1, the sides of a square are increasing at a rate of 2 inches per minute. Part A, how fast is the area of the square increasing when the sides are 3 inches? So let's go back to the problem, the sides of a square. So the first step, if possible, is to draw a diagram, and the geometric shape is a square. So let's go ahead and draw a square, and a square has equal side lengths, so I'm going to call the side lengths S. And we're told that the sides of a square are increasing at a rate of 2 inches per minute. So once we've drawn our diagram and we've labeled our diagram with variables, so the side lengths are changing, they both need to be variables, so S and S, the same variable because it's a square. Now I want to label my givens. So what I've been given in this problem is a rate. The side of the square is increasing at a rate of 2 inches per minute. Well, I called the side of my square S. So in mathematical notation, I have been given ds dt. The rate of change of the side with respect to time equals 2 inches per minute. So I wanted to translate my given information in words. So I know I was given in words the side of a square is increasing at a rate of 2 inches per minute into mathematical notation. So I want to identify the givens and the want. So what do I want to find? In part A, how fast is the area of the square increasing when the sides are 3 inches? So I want the rate of change, because I'm asked how fast, the rate of change of the area of a square. So we denote area with the variable a, so I want dA dt. I want the rate of change of the area with respect to time when the sides, when S equals 3 inches. That's what I want. So I wrote my givens and my wants. So the next step is to find an equation that relates the variables. So my variables are A and S, area and side. So the area and the side relationship in a square is that area equals side squared. So once I write the equation, if possible, I fill in any constants. Well, the variable a is not a constant, it's changing. The area is changing because S is changing as well. The side of the square is changing. So I cannot replace either a or S with a number yet. They are both changing quantities. So at this step, I have to take the derivative with respect to t of both sides. So d dt of a and d dt, the derivative with respect to time of s squared. So now, this is implicit differentiation. The variables here don't match. So the derivative of a would be 1, but since the variables don't match, I need to include dA dt equals, so now here the variables don't match. The derivative of s squared is 2s, but I also need to include a ds dt. So I wanted dA dt when the side is 3 inches. So I'm about to plug 3 into this s right here, and I'm given ds dt is 2 inches per minute. So in other words, dA dt is 2 times 3 times 2. So I'm filling in my s, which was 3 inches, and my ds dt, which was 2 inches per minute. So what I also want to do here is I want to include units. So the 3 inches had the units of inches, and my ds dt had units of inches per minute. So this is inches times inches per minute. So in other words, the final answer would be, well, I multiply all my numbers, so 2 times 3 times 2 is going to give me 12. So my answer is going to be 12, but my units, well, this is inches times inches, so this is like inches over 1. So inches times inches is inches squared per minute. So that should make sense because I wanted the rate of change of an area. Let's remember an area is a unit that's squared, so inches squared, over a time, which is in minutes. So the rate of change of the area with respect to time, exactly when the side length is 3 inches, is 12 inches squared per minute. So that is dA dt. So now let's look at part B. How fast is the area of the square increasing when the square has an area 25 inches squared? So I still have the same given, so my given, again, I'm just going to put G, is ds dt is 2 inches per minute. And I still want to know how fast the area of the square is increasing. So I still want dA dt, but what has changed is I want dA dt when the square has area 25 inches squared. So dA dt when the area A is equals 25 inches squared. So previously I was told I want dA dt when S equals 3 inches. This time I want dA dt when A equals 25 inches squared. So I in fact have to use the same relationship because I want dA dt, so A equals S squared. So I'm actually going to use the exact same formula, dA dt equals 2S ds dt. But I'm going to be missing something. I'm going to be missing an S. So I have a ds dt still. That's quantity has remained 2. But I don't have a side length. I have an area. But if my area is 25 inches squared, I know that area is the same as side squared. So if area has to be 25 inches squared, then sine squared has to be 25 inches squared. So if I take the square root of both sides, I'll get s equals plus or minus 5, but since this is a distance, it has to be positive. So s has to be 5 inches. So in being given the area was 25 inches squared, that's like being told that the side length had to be 5 inches because side squared, 5 inches times 5 inches, is 25 inches squared. So I can now take this quantity of 5 inches and substitute it into my side S. So my units will again be inches, that corresponds to 5, and then inches per minute, that corresponded to 2. So now I'm going to have 20 inches squared per minute. So how fast is the area of the square increasing when the square has area 25 inches squared? That's the same as like saying when the side of the square is 5 inches. So our answer there is 20 inches squared per minute. Okay, let's move on to a third example. The radius of a spherical balloon is decreasing at a rate of 2 inches per second. Part A. How fast is the volume of the balloon decreasing when the radius is 5 inches? Alright, so the radius of a spherical balloon, so we're talking about a sphere, so if possible we draw a picture. My 3D pictures are not spectacular, so sorry. Alright, good enough. So it's supposed to look like a sphere, and we're interested in labeling the radius. So the radius is going to be r. And we're told that the radius is decreasing at a rate of 2 inches per second. So we want to write down our given. We've been given dr dt is negative because the radius is decreasing at a rate of 2 inches per second. So given dr dt is negative 2 inches per second, we want to know how fast the volume, so I want the rate of change of the volume, we usually call volume V, so we want dV dt when the radius is 5 inches. So dV dt when r equals 5 inches. So now we write an equation that relates our variables. Our variables are V and R. The volume of a sphere is volume equals 4/3 pi r cubed. So pi is a constant, 4/3 is a constant, so my only variables are V and R. Both are changing. The volume is going to be changing because the radius is decreasing. So once we have this formula, we can't plug in any numbers for V and R yet. Now we take the derivative with respect to both sides, with respect to t of both sides. So ddt of V and ddt of 4/3 pi r cubed. So ddt of V would be 1 dV dt, so just dV dt. And now the derivative with respect to time of 4/3 pi r cubed. So r cubed is the variable. So the derivative of r cubed is 3r squared. So 3 and 4/3 would become 4. And I'm just going to bring down the pi, and we just reduce the exponent by 1. So 4 pi r squared, and then we need to include dr dt because this is implicit differentiation. Okay, so now we want dv dt when r is 5 inches, so I'm going to plug 5 into this r, and then -2 inches per second into dr dt. So 4 pi, and then r is 5 inches, and I'm actually going to put inches in there so I can emphasize the units, and then dr dt is going to be -2 inches per second. So this is 4 pi, 5 inches squared. Well, the 5 gets squared to be 25, but inches get squared as well. So I have inches squared, and then I have times -2 inches per second. So now I have 4 times 25 times -2, so that's going to be -200, multiplying the numbers without pi. So now I can just include the pi. And now I have 3 copies of inches, so inches squared and inches, so this would be inches cubed over seconds. So dv dt is -200 pi inches cubed per second. And we needed the top units to be in terms of volume, so volume is inches cubed over a time in seconds. And dv dt needs to be negative because the question asked how fast is the volume of the balloon decreasing. And we had a decreasing rate here as well. So we did need our final answer to be a negative quantity. Alright, so now part B. When the volume of the balloon is 20 inches, what is the radius? So let's read that again. When the volume is 20 inches cubed, so when V equals 20 inches cubed, what is the radius? So I'm being asked for, I want just R. I want the radius. So this is actually not even a calculus problem, and it's really an understanding the difference in what you've been given. So when the volume is 20 inches cubed, so that's what I've been given. Oops, this is what I've been given. That volume equals 20 inches cubed. I want the radius. So I still have to come up with an equation that relates to the sides, or the information, 4/3 pi r cubed. But now all I need to do is substitute in 20 into V and solve for R. So 4/3 pi r cubed. So I'm just going to multiply both sides by 3/4. So this is going to be 60 over 4, which is 15. So 15 equals pi r squared. So I'll divide both sides by pi. So 15 over pi equals r squared. So if I want r equals the square root of 15 over pi. And it would be plus or minus, but because the radius is positive, it's just going to be the square root of 15 over pi. And the units of my radius are going to have to be in inches. So radius is just the 1 unit of inches. So r would be the square root of 15 over pi inches. And this problem was really just to illustrate the difference in being asked for a rate. So in this problem, how fast is the volume of the balloon decreasing, versus here, what is the radius? Not how fast is the radius changing or what is the rate of change of the radius, just what is the radius. So I would want that to be in units of inches. Alright, example 4. The radius of a circular cone of fixed height 30 centimeters is increasing at a rate of 3 centimeters per second. How fast is the volume increasing when the radius is 8 centimeters? So we've reached a trickier example now. The radius of a circular cone. So let me attempt to draw a circular cone. That's the shape, that's the geometric object. So a circular cone, trying to draw like an ice cream cone looking thing. So the radius is going to be this distance here. This is r. And this cone has a fixed height. So the height here is 30 centimeters. So that's the height. So the radius of the cone with fixed height is increasing at a rate of 3 centimeters per second. So this is like an extended sentence here, and that's where students get confused. But we're being told that the radius of the circular cone is increasing at a rate of 3 centimeters per second. So what have we been given? We've been given dr dt. The rate of change of the radius is 3 centimeters per second. And we're being asked to find, we want, how fast is the volume increasing when the radius is 8 centimeters? So I want the rate of change of the volume. How fast is the volume changing when the radius r equals 8 centimeters? So now I have to relate the variables. Well, the volume of a circular cone is V equals 1/3 pi r squared h. Alright, so I have 3 different variables here. And now I want to talk about, once you write the equation, if possible, you want to substitute in any quantities that are constant, that are not changing. So the volume of this cone is changing. So what's happening? Let's think about what's happening. The radius is increasing. So this r, imagine this ice cream cone is getting fatter. So the radius is expanding. So this ice cream cone is getting wider. But we were told that the height is not changing. The height is always going to be 30 centimeters. Well, if the radius is expanding, the volume is expanding. So I cannot replace v with anything. V is changing. I can't replace r with anything. R is a changing quantity. The radius is expanding. But the height, that's never changing. The height is always 30 centimeters. So that's a constant quantity. So I can replace h with 30. And once we do that, I'll explain why we would have really needed to do that and why it would have made our lives a lot harder to not have done that. So if we didn't replace h with this fixed number 30 here, when I took the derivative with respect to time of both sides here, the derivative of v, that's dv dt. But if I were to take the derivative over here on the right side, r squared and h are 2 separate functions. So I would have had to use the product rule along with implicit differentiation to differentiate this. And when I differentiated h, I would need dh dt, which isn't explicitly given, and it would make our lives a little harder to think about. So at this step, when you find the equation, if there's any quantities that are not changing, we can replace them numerically instead of using the variable. So now let's rewrite this. Volume equals 30 times 1/3 gives me 10. So 10 pi r squared is a lot easier to deal with. So now I take d dt of both sides. So d dt of v and then d dt of 10 pi r squared. So I'm going to go ahead and bring the work up here. The left side is dv dt. And the right side, r is the variable. So the derivative of r is 2, or r squared is 2r. So times 10, that's going to be 20 pi r. And then we need to include the dr dt for implicit differentiation. And now I wanted dv dt when r was 8. So dv dt is 20 pi, this is an r, whoops, this is an r. So my r was 8 centimeters, and then dr dt was centimeters per second. So 3 centimeters per second. And the 30 actually came with the unit centimeters. So that's where our extra centimeters is going to have to come in to play. So this 20 actually had a unit of centimeters as well. So multiplying all of my numbers together, I'm going to have 24 times 20 times pi. So 480 pi. And then I have centimeters cubed per second. And I needed centimeters cubed. That's why I went back to make sure that I didn't really lose a unit. I just forgot to carry it over with this 30 centimeters of height because I need this to be a volume. So centimeters cubed is a volume over my time in seconds. So 480 pi centimeters cubed per second is the rate of change of the volume with respect to time exactly when the radius is 8 centimeters. All right, example 1. Water pours into a fish tank at the rate of 3 feet cubed per minute. How fast is the water level h rising if the base of the tank is a rectangle of dimensions 2 by 3 feet? All right, so the image has already been drawn out for us. Here's the fish tank, and the base, we're told, has dimensions 2 feet by 3 feet. And we're given that water pours into the fish tank at a rate of 3 feet cubed per minute. So what we've been given here is we've been given dV dt. So we've been given the rate of change of the volume. And even though we weren't told the word volume, we would have to recognize that based on the units. So feet cubed, dV dt, per minute. So the rate of change is 3 feet cubed per minute. And we want to know how fast the water level h is rising. So we want dH dt, the rate of change, how fast is the water level rising. So this is what we're interested in finding. So this is going to form a rectangular prism, and the area of a rectangular, or the volume of a rectangular prism, is length times width times height. So if we call L 3 and then the width 2, the length and the width are not changing because the base is always 3 by 2. So this becomes 3 times 2 times h. So the volume can be represented by 6h. So now I want to take the derivative with respect to time of both sides because the volume and the height are both changing. So ddt of v and then ddt of 6h gives me the relationship that the rate of change of volume with respect to time is 6 times the rate of change of the height with respect to time. So using implicit differentiation, and I was given that the volume is 3 feet cubed per minute, or the rate of change of the volume, so 3 can be input in for dV dt, and that has to equal 6 dH dt. So now if I want to solve for dH dt, I divide both sides by 6. So the 6's will cancel, this reduces to 1 over 2, so dH dt is 1 over 2, and my units, this is just one part of my three-dimensional volume, so my units have to be in feet per minute. So dH dt is 1/2 feet per minute. All right, in example 2, we're going to go over the classic ladder problem, which is the typical example to go over first in a related rate section. But I do think it actually has quite a bit of pieces of information to it, so I would consider it a more challenging example. What we have is a 13-foot ladder that's leaning against a wall. The bottom of the ladder is 5 feet from the wall at time t equals 0, and the bottom slides away from the wall at a rate of 3 feet per second. Find the velocity of the top of the ladder at time t equals 2 seconds. So we have a 13-foot ladder leaning against a wall. So this right here is going to represent our ladder, and this vertical line, this vertical part to the triangle, is going to represent the wall. So here I'm going to go ahead and call this ladder Z, and the length of Z is a constant 13 feet. So we don't have a ladder that slides in length. The ladder's length is always 13 feet. And so let's go ahead and call this X and this Y. So Y is going to be where the wall would be, and Z is the ladder. So we're told that the bottom of the ladder is 5 feet from the wall. So again, this vertical line represents the wall. So the base of the ladder, X, is 5 feet. And this is when time equals 0. So at time 0, I have this 13-foot ladder. Let's say it's leaning up against a window, and the base of the ladder is exactly 5 feet from the wall. And what's happening is, imagine that someone's pulling the base of the ladder away from the wall. So the ladder is moving in this direction, or the base, I should say, is moving in this direction to the right and sliding away from the wall at a rate of 3 feet per second. So if we call this distance x, then the rate of change of x, dx dt, is 3 feet per second. So that's what I have been given. So I'm sort of drawing all my givens on the graph. So what I'm interested in finding is the velocity of the top of the ladder at time t equals 2 seconds. And here's where I think it is a little bit of a complicated question, is because we're looking for the top of the ladders here. We're looking for how fast the top of the ladder is sliding down. So essentially, we're looking for dy dt. So the rate of change of y. So y meaning the height from the top of the ladder to the base of the floor. That's the distance that I called y. So I would be looking for, I'm in search of dy dt. That's what I want. But specifically when time is 2 seconds. So not at this starting point. So not at time 0 where the ladder's just resting against the wall that's 13 feet long and the base is 5 feet from the wall. I want to know what's happening 2 seconds later. And a lot of students are going to think, well, if I pull the bottom at a rate of 3 feet per second, well, then the top is going to be moving at the same rate of change. But that's not the case. And what I want you to think about is if you really think about pulling a ladder, so you might be sort of hesitant to pull the ladder because when you start to pull it, you know that at some point it's going to fall down and hit the ground really fast. So dy dt is actually going to have a rate of change that is going to increase. So the rate of change is going to have an increasing rate of change. It's going to slap and hit the ground as you continue to pull the base of the ladder away from the wall. So they're actually not the same, and that's what a lot of students tend to go to, is that these are the same, but we're relating to different rates. So we want to know how fast the velocity of the top of the ladder is moving at t equals 2 seconds. But our diagram, that's when t equals 0. So that's why I have this second triangle drawn here, because what I have to do is I have to think about what's going on at t equals 2 seconds. Well, the ladder's not changing, so z is still going to be 13 feet. That's the same. But after 2 seconds has passed, if I'm pulling the ladder, they started out as 5 feet from the wall, and I'm pulling it away at a rate of 3 feet every 1 second. Well, if the original distance was 5 feet from the wall, after one more second, it would be 8 feet from the wall. After another second, we're going to add 3 more to that, so it would be 11 feet from the wall. So my new x is going to have to be 11 feet. But my dx dt is the same. So the rate of change, how fast I'm pulling it, is a constant. Dx dt is still 3 feet per second. So now I have to think about, well, what's the y value here? So I'm still interested in finding dy dt at this moment in time when x is 11 feet, z is still 13 feet, and eventually I'm going to need to find y, but we'll get to that. So this forms a right triangle. Again, I want to find dy dt at this moment in time. So I'm dealing with these numbers, 11, 13, and eventually I'm going to have to solve for y. But for now, I want to relate the variables. So x, y, and z are related by the Pythagorean theorem. So x squared plus y squared equals z squared. Now, if possible, I want to plug in any constants, things that aren't changing. And we've said that no matter what, the length of the ladder is 13 feet. But x and y are changing. The rate of change of the height of the ladder and the distance from the ladder, the base of the ladder to the wall, are changing. So I can plug in 13 for z. So this would be 13 squared, so 169. So now I have to take the derivative of both sides with respect to time. So d dt of x squared plus y squared, so the whole left side, and then d dt of 169. So the right side, the derivative of a constant is 0. The left side would be 2x dx dt plus 2y dy dt using implicit differentiation. And so now I'm solving for, let's change colors here, I'm solving for dy dt. So in order to find dy dt, I'm going to have to plug something in for y, for dx dt, and for x. But I have quantities for x and dx dt. So 2 times my x value at 2 seconds is 11. So 2 times 11. Dx dt is 3 plus 2 times. So now here's where I have to solve for y. So to solve for y, I have to use the Pythagorean theorem. So specifically, when time is 2, the Pythagorean theorem gives me x squared, so 11 squared plus y squared equals 13 squared. So 11 squared is 121 plus y squared equals 169. So y squared is going to be, if I subtract 121 from 169, it's going to be 48. So y is going to be the square root of 48. So we'll go ahead and leave it for now as the square root of 48. So that's my value for y. Of course, it would be plus or minus, but I need it to be the positive version. It's a distance. So let's go ahead and plug the square root of 48 in right here for y. And then dy dt equals 0. So, oops, that's an x. That should be a t. So dy dt. So I'm solving for dy dt. So that means I'm going to need to subtract this quantity, 2 times 11 times 3. So that's 6 times 11. That's 66. So I'm going to have 2 times the square root of 48 dy dt is going to have to equal negative 66. And then I'll have to divide by 2 times the square root of 48 if I want to get rid of that quantity to isolate dy dt. So dy dt, without simplifying anything, is negative 66 over 2 times the square root of 48. So if we were to simplify this, and I'm not going to rationalize the denominator, this is 33 over 8 radical 3. And of course I could rationalize, but I'm not going to do that for now. I'm going to leave my answer like this and be sure to include, oops, I forgot the negative, be sure to include my units. So my units would be the same as dx dt, feet per second. So feet per second. And we need to ask ourselves, why is this quantity negative? Well, this y value here that represents the top of the height of the ladder to the floor, this distance is getting smaller because the ladder is coming down to hit the ground. So that's why this is a negative quantity. So this is considered to be where you intro related rates. This type of problem is considered to be a basic problem, but I do think it is a little bit complicated because we do have to think about what's going on at 2 seconds, whereas they give you introductory information when time equals 0 seconds. Alright, example 3. Water pours into a conical tank of radius 4 feet and height 10 feet at a rate of 10 feet cubed per minute. Part A. When the water level is at 5 feet, how fast is the water level rising? Alright, this is definitely an advanced problem. So we have water that's pouring into a conical tank. So here's the image, the pink portion, the bigger pink portion, that's the cone that we're pouring water into. So what I want you to imagine is if you've ever gone to the fair and you've gone up to the little Sparklets drinking station and the cups are like snow cones. So that's what's happening here is we kind of have a snow cone cup and we're pouring water into it. And the cup itself has a radius 4 feet. So the radius of the actual cup is 4 feet and the height is 10 feet. So that's given right here. The height of the actual cup is 10 feet. And the rate at which the water is pouring in. So water pours into this conical tank with these dimensions at the rate of 10 feet cubed per minute. So let's write down what we've been given. We've been given dv dt. And that is apparent in the units. 10 feet cubed, so the rate of change of a volume with respect to time. So 10 feet cubed per minute. In part A, we're asked, when the water level is at 5 feet, how fast is the water level rising? So this blue portion here represents the water. So the height of the water is a variable. It's changing. So we have to label it with H. And then we have a radius of the water that's changing, so we have to label that with R. So where students get confused here is the fact that there's a fixed height, that's the height of the actual cup or the cone, that's 10, and a fixed radius of the cone that's 4. But it's almost like we have two cones because the shape that the water takes on when poured into a cone is also a cone. So the height of the cone of water is changing, and that's H, and then the radius of the cone of water is r, and that's changing as well as the water is pouring into this cup. So when the water level is at 5 feet, so that meaning this h, when this h is 5 feet, how fast is the water level rising? So at that one moment in time, when the height of the water is 5 feet, how fast is the water level rising? So I'm looking for, here's what I want. I want dH dt when, and I'm going to start to use this notation, when the height of the water is at 5 feet. So I want dH dt when h is 5, given that the water pouring in is 10 feet cubed per minute. That's the rate that the water is pouring in. All right, so now we have to relate the variables. So I want to relate R and H. Those are the two quantities that I'm considering. Now I am given this extra piece of information, this 4 and 10, and we'll see how that comes into play in a second. But right now I want to relate the variables. So the variables are V and H, the volume of a cone, and I'm thinking about the volume of the water part in the cone. The volume of a cone is 1/3 pi r squared h. Now, the volume is changing. I cannot replace V. The height of the water is definitely changing, so I can't replace H with a number. And R is changing as well. If the height of the water is rising, then this radius here of the water, this blue portion, this radius would be getting bigger as this cone continues to fill up to the top. So I have V, R, and H that are all changing. So I can't substitute any number in to replace them. Now, at this point, if you're copying it down as I'm writing, I don't want you to copy down this next part. At this point, if you don't do the necessary substitution that we're going to do in a second, if you just jump straight to taking the derivative of both sides. So what I'm going to do is I'm going to show you what would happen, but I don't want you to write this down because this is not the correct method. I would take d dt of both sides. So d dt of pi r squared h. Now the left side is fine, you'd get dv dt, but the right side, whoops, I lost the 1/3. I could consider 1/3 pi r squared one function and h another function, and I'd have to use the product rule. So I'd have to say 1/3 pi r squared, so the first function, the derivative of h is dh dt, plus the second function h times the derivative of the first, the derivative of 1/3 pi r squared would be 2/3 pi r dr dt. So here's the problem. We're solving for dH dt. We want this quantity. So if I want this quantity, I have to substitute in something for dV dt. No problem. I have that quantity. I have to substitute something in for R. Do I have R? So let's pause and think about that. dH dt is what I'm solving for. H. I have H. H is 5. I need R again, and I need dr dt. So R and dr dt are quantities that I don't have, that I don't know anything about. So that's the problem, is that if I were to just at this step go, I can't plug anything in, any constants for V, R, and H, so let me just jump straight to the derivative. I should recognize I'm going to have a problem, because when I differentiate R, I'm going to need a dr dt, and I'm also going to need an R, and I don't know anything about those two quantities, R or dr dt. So this is not the correct method, unless I were to be given some information about R and dr dt, which may happen in a different problem. So for this problem, that method is not going to work. So here's what I have to do, and here's why I'm given the 4 and the 10. If you see what this figure says, by similar triangles, H over R, so I actually have two triangles here. Here's one, and I'm going to do the other one in a different color. Here's another one. So by similar triangles, I have this relationship that H to R, so H over R, is equal to 10 over 4. So the height over the radius, and then the height over the radius again. So I have this relationship, H over R equals 10 over 4. So what I really want to do is I want to get rid of this R. This R is a problem because it got me an R and a dr dt that I didn't know what to do with. So to replace this R, I have to rewrite R so it's in terms of the variable H. So I have and do it up here in the corner, I have h over r equals 10 over 4. So if I cross multiply here, I know that 4h equals 10r. And I want to solve for r so that I can replace this r with h's. So I'm going to divide both sides by 10. So the 10s will cancel. So r equals 2 over 5h. So now I can take 2 over 5h and substitute it into this r. So v equals 1/3 pi. R is 2 over 5h squared h. So now this whole thing's in terms of h, so let's simplify it. I'm going to get 1/3 pi. 2/5 squared is going to give me 4 over 25. Because I'm squaring 2 over 5, I have to square h. So h squared h. So my final volume formula is going to be 4 over 75 pi. So I'm multiplying 4 over 25 and 1 over 3 in pi. And then h cubed. So this is now the volume formula I would rather deal with than this one, because this one had the r, which was a problem, because it would give me a dr dt and an r that I have no information about whatsoever. But now I can differentiate this with respect to time. So ddt of v and ddt of 4 over 75 pi h cubed. So this is dv dt equals, if I take the derivative here, if I bring the 3 to the front, because I'm differentiating h cubed, I'm going to get 12 over 75 pi h squared dh dt. And now I want dh dt when h is 5. So I'm going to go ahead and plug 10 into dv dt. So 10 equals 12 over 75 pi. H is 5. 5 squared dh dt. And I'm sorry I ran out of space. I'm going to try to fit it up here. So I'm solving for dh dt. So where I left off is I'm going to multiply both sides. Actually, let's simplify this. This would be a 25. So the 25 and the 75 would cancel. This is just going to give me 12 over 3. 12 over 3 is 4 pi. So this is 10 equals 4 pi and then dh dt. So I just simplified. 5 squared was 25. 25 over 75 would give me 1 over 3. But now 12 over 3 is 4. So 4 pi is what's left, dh dt. So in other words, dh dt is 10 over 4 pi. My units, it's 1 unit of a volume. So it's going to be feet per minute. So 10 feet per minute is dh dt. So 10 over 4 pi feet per minute is the rate of change of the height. That's how fast the water level is rising at the moment the water level is 5 feet. So now let's just take a look at part B. As time passes, what happens to the rate at which the water level rises? And then explain. So this was part A. All of that was part A. So now part B is really just a conceptual understanding. So go back to thinking about this as a water cup, like the little Sparkletts water cup, and imagine pouring water into this. So the rate of change of the height of the water, when you first start pouring water into it, it fills up really fast because there's less volume to occupy at the base. So when you start pouring water into this, all of a sudden it pours really fast, and then the height starts to slow down. So it just like shoots up and then starts to slow down as there's more volume to occupy as we get closer to the top. So as time passes, what happens to the rate at which the water level rises? The rate slows down. So the rate ends up slowing down. So that's the answer to part B. The rate slows down. And the reason rate slows down because more volume to occupy. So as this cup starts to fill up, there ends up being more volume that I have to occupy, so the height, the rate of change of the height slows down. So first, dHdt fills up pretty fast, and then as we get to the top, the height increases but slower. So the rate slows down because there's more volume to occupy. All right, example 4. A person is tracking a rocket 10 kilometers away in vertical flight through a telescope. If, when the angle theta is 60 degrees, the rate of change of the angle is 0.5 radians per minute, how fast is the rocket traveling? All right, so this picture would come along with the information. So here's the person on the ground. They're tracking a rocket that's 10 kilometers away. So the distance from the person to where the rocket was when it was about to launch is 10 kilometers. And the rocket is in vertical flight, and so he's looking at it through this telescope. So at the exact moment when the angle is 60 degrees, so when this angle theta is exactly 60 degrees, the rate of change of the angle, so the angle is of course going to be increasing as the rocket gets higher in the air, so the angle is changing. So the rate of change of the angle is 0.5 radians per minute. So at the exact moment when the angle is 60 degrees, how fast is the rocket traveling? So if the rocket started out on the ground, its height can be measured by this changing variable y. So here's what I'm given. I'm given the rate of change of the angle. We call it the angle theta. So I'm given d theta dt is 0.5 radians per minute. And I want to know how fast the rocket is traveling. So if I call this distance y, how fast y is changing is how fast the rocket's traveling. So I want dy dt when theta equals 60 degrees, at the moment when the angle is 60 degrees. So now I need a way to relate the variables. So the variable are theta and y, so theta being the angle and y being this distance here. So notice I also was given the distance from the man to the base of the rocket was 10. So I have an angle, its opposite side because this forms a right triangle, and its adjacent side. So the opposite over adjacent is the tangent function. So the function I'm going to use to relate the variables is tangent theta equals opposite. So the opposite is y over adjacent. So we could give this a variable name if we wanted to, but this is unchanging, so I would replace it with the unchanging quantity 10 anyways. So let's just put y over 10. So now theta is changing, y is changing. Now I could jump straight to taking the derivative with respect to time of both sides. So ddt of tangent theta, and then ddt, I'm going to rewrite y over 10 to be 1/10 y. So now when I take the derivative of tan theta, the derivative is secant squared theta d theta dt, and the derivative of 1/10 y is just 1/10 and then dy dt. So I'm interested in finding dy dt, so I need to substitute something in for theta and d theta dt. So secant squared theta is 60 degrees. D theta, whoops, that's supposed to say d theta dt, and it says d theta, sorry about that. D theta dt is 0.5 radians per minute. So what I'm going to do is I'm going to rewrite that as 1/2. And then that has to equal 1/10 dy dt. So secant squared of 60 degrees, I'm going to rewrite that as 1 over cosine of 60 degrees quantity squared. And this is still times 1/2. And then what I'm going to do is multiply both sides of this by 10. So this is like 10 over cosine 60 degrees squared times 1/2. And that's going to equal dy dt. So the rest is a matter of simplifying. So this is 10 over cosine of 60 degrees, or this is like cosine of pi over 3, is 1/2 squared, and then this is times 1/2, and this is dy dt. So 1/2 squared times 1/2. So if I wanted to do this, one of the 1/2s will cancel, so it's like 10 divided by 1/2, which is like 10 times 2 over 1, so this quantity is 20. So dy dt equals 20, and my units are going to have to be kilometers per minute. So if I think about how fast the rocket's traveling, my units of distance were in kilometers, so I wouldn't want my answer to be in radians. Radians is a measurement of an angle, not of a distance. So my distance is going to have to be kilometers per minute. So dy dt, or the rate of change of the rocket, how fast the rocket's traveling, is 20 kilometers per minute. And if we think about that in a real world scenario, that makes sense. The rocket should be traveling pretty fast. So 20 kilometers per minute is pretty fast. All right, in this last example, example 6, there's a very similar problem on a previous AP exam where instead of trains, we're dealing with ships. But this one, we have one train traveling west toward Denver at 120 miles per hour, while a second train travels north away from Denver at 90 miles per hour. So I'm going to stop and look at the image that's been given. So I'm going to go ahead and label my givens on the graph. So I'm told that one train is traveling west toward Denver at 120 miles per hour, and the second train is traveling north away from Denver at 90 miles per hour. So notice that this distance from the Denver station to the train traveling north has been called y. And this distance of y is going to be an increasing distance because the train is traveling north away from the Denver station. So when I've been given 90 miles per hour, what I've really been given is dy dt. And it would be a positive quantity because y is getting bigger. So the rate of change of y is going to be a positive quantity. As opposed to this train that's traveling west, if I call this distance away from the Denver station x, x is getting smaller. So this quantity I've been given is dx dt, but it would in fact be a negative quantity because x is getting smaller. So at time t equals 0, the first train is 10 miles east and the second is 20 miles north of the Denver station. So this image corresponds to when time is 0, and the first train is 10 miles east. So this distance right here is 10 miles, so 10 miles east of the Denver station, and this train is 20 miles north of the Denver station. Calculate the rate at which the distance between the two trains is changing at time t equals 0. So I'm interested in finding the rate of change of L. So this variable, the distance between the two trains, is called L. And this should also look somewhat familiar to the very first example where I said that you left your house and your parents left your house at a particular time, and we wanted to know the rate of change between the two of you at a particular moment in time. So that's what we're doing in this problem. So here's what I want. I listed my givens on the graph, but what I want is dl dt at t equals 0. So I need a way to relate all of my variables. So my variables are x, y, and L, and this forms a perfect right triangle. So my formula is x squared plus y squared equals L squared. And each of the variables are changing. Each of those lengths are changing. So I can't replace them with constants. I just have to take the derivative with respect to x, or t, with time, on both sides. So ddt of x squared plus y squared and ddt of L squared. So I'm going to get 2x dx dt plus 2y dy dt equals 2l dl dt. And so since there's a 2 in everything, so on this left side I could factor out a 2, and then I could divide both sides by 2. So in other words, we can pretty much ignore the 2's altogether. So this is just x dx dt plus y dy dt equals L dl dt. And I want to find dl dt, that was the goal. So I need to plug something in for each of the other quantities. So x was 10, dx dt is negative 120, y is positive 20, dy dt is 90, and L is something I'm going to have to search for. So L at time 0 can be found using the Pythagorean theorem with the side lengths 10 and 20. So 10 squared plus 20 squared would give me the hypotenuse squared. So this is 100 plus 400. So this is 500 equals L squared. So if I take the square root of both sides and only consider the positive answer, L is the square root of 500. Whoops, the square root is what I meant to do. The square root of 500, and then dl dt. So now this is a matter of simplifying. So this is negative 1200 plus 1800 over the square root of 500, and that's dl dt. So I divided by the square root of 500. So this is 600 over the square root of 500. And what I'm going to do to determine the plausibility of my answer is plug this into my calculator. And I get 26, so I should put approximately, I get 26.832. So whenever I use my calculator, I always want to go to the thousands place. And here I just truncated. So I just cut it off after 3 places past the decimal. So 26.832 miles per hour would be dl dt.